Welcome to this lecture in the ongoing series of lectures on real analysis. We'll be continuing with our module on integration. Last time we introduced a bunch of different notations and concepts. So we started with the bounded function, and let's say we call capital M the supremum of f over its entire domain and little m as this infimum of f over its entire domain. We defined a subdivision of a closed interval as just a finite list of real numbers with the property that the first guy is actually the left hand point, the last guy is the right hand point, and the things in between are in an increasing order. Alright, so once you have a subdivision sigma of the domain of f, then we define the upper sum. So this we call the upper sum of f corresponding to sigma by this recipe. So we have these two things in this notation, in the summation. What is this? This is the supremum of f over the ith part of the subdivision. So if our subdivision is depicted, let's say this is a naught equals a and this is an which is equal to b, a1 dot dot ai minus 1 dot ai and dot dot dot. So this is the ith part of the subdivision, and the supremum of f over the ith part is written this way. The length of the ith part is written that way, and this is the length of the ith part, basically this point minus that point. So we saw that, so this is some quantity, and we saw a geometric interpretation of it, that you can think of it as an upper area. So if the graph of the function is like this, then we saw that you can think of it as the areas of such rectangles. So it's kind of an upper approximation. It overestimates the quote-unquote area under the curve in some way. The how much it approximates, that we are not commenting on. It is some things to be thought of as some upper approximation to the actual quote-unquote area under the curve, if there is such a thing. Similarly, we have the lower sum. So this is the lower sum of f corresponding to sigma, and similar things. So this mi is the infimum over the ith part. That's all. That's the only difference. So it is an underestimation of the actual area under the curve, whatever that means. And then we define the upper integral of f as the infimum of all the upper sums that are possible by taking all the subdivisions. And so one can think of it as the quote unquote the best upper approximation to the area under the curve. And similarly, the lower integral as the supremum over all subdivisions of the lower sum. So this is the best lower estimate to the area under the curve. And we saw that the upper sum dominates the lower sum, and they are in fact themselves sandwiched between these two values. What was m? Recall m is this and little m is that. So they are themselves sandwiched, and all of these were very easy implications. One of the things we did down the line was that if suppose tau refines sigma, so what do we mean by refines? We mean that tau has some extra points. Sigma is some bunch of points. All of them are there in tau, but some extra points may also be there in tau. So that's the refinement. And we saw two properties, that if tau refines sigma, then the lower sums behave in the same fashion. So we just write an s here, but the upper sum flips out. So it's in the opposite direction, the inequality. And again, this is intuitively obvious, nothing to be learned here. You don't need to remember any of this. This is just very, very intuitively obvious stuff. Okay, so these are the problems. And now let us move on to today's lecture. And what we want to prove is something called Darboux's theorem. And let me say a few words as to what is the point of this theorem before we state the theorem. So we have defined these weird looking concept, although it's not really all that weird. But this definition does not give a hint as to how to calculate the upper integral. The upper integral is the infimum over some bunch of things, over infinitely many things. So how would one go about calculating this? Darboux's theorem gives us a way to potentially calculate this once you have a good handle on what f is. Similarly, you can calculate that using Darboux's theorem. So that is what we are going to do. Before we state the theorem, we need to develop some basic facts, and then we will get to the theorem. So here is the first very simple fact. So we start with the bounded function on the closed interval a comma b, and let tau be a subdivision of the domain of f, and let c be some point strictly between a and b. Let rho be the subdivision of the domain of f obtained by inserting c in sigma. So this is a kind of an informal phrase, but what does this mean? This just means that you take sigma, whatever that bunch of numbers that there are in sigma, you just put c and make a new subdivision. So that's what this means. So it is a refinement of, no, I said sigma where I meant tau. So it is a refinement of tau, right? And so rho is obtained by just inserting c in tau. And what we want to show is the following. So let supremum of this thing be at most k. Then since f is bounded, this is some real number. I mean, the supremum is some real number. So let's say it is at most k. So then we want to claim that the two upper sums are not very far apart. So I did not mention what is this. Let me recall what is that. So norm of, if you have a subdivision, then norm of is the max of Li sigma, where I goes from 1 to n. So Li sigma is here, or rather I have defined it here, and the maximum of the length of all the parts is the norm of sigma. We defined this the last time, but I forgot to recall it in the beginning, so that's what I'm doing. Okay, so here is your statement. And well, since rho is a refinement of tau, there is no need for putting absolute values. This already is at least as much as that. So I could just drop absolute values, but I have put it there just for some psychological, at least for my own psychological well-being. What is it saying? It says that by just inserting one point in a subdivision, you don't really change the upper sum too much. That's the message of this lemma, and let's prove it. It's very, very easy to prove. So let tau be equals to a naught up to an, and if c is equal to ai for some I, then tau equals rho, and therefore we are done, and we are done. So we may assume that c is not equal to ai for any I, and then what we can do is let's say this is a naught, then somewhere a1 dot dot dot, there's ai minus 1, then you have a c somewhere in between these two things, ai dot 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 an. So let's say c is between ai minus 1 and ai. Since it is not equal to any of these folks, it has to be strictly between one of the two, and let's say that index is I. Alright. So okay, so before we go on, let us define, let m prime be supremum of f over this first part. So the supremum of f over this region is m prime, and the supremum of f over this region will be m double prime. Let me write that. Okay, so we have defined these two things. We'll see why are we even considering that. So here is what we want to estimate, s tau minus s rho. This is what we want to estimate. But note that it is all the action is happening here. In this region and in that region, tau and rho are exactly the same. I mean, they behave exactly the same way. So we just need to make sure that we understand what am I going to write next. So this is equal to mi ai minus 1 minus m prime c minus ai minus 1 plus m double prime ai minus c. So you just need to understand this equation. What is happening is this is the contribution coming from s tau for this region. Mi is the supremum of f over this region. As I recalled in the beginning, this will be the notation that we'll be using. Maybe I'll just write it here. So this is equal to supremum of fx over the ith region of tau. So that's what this guy is. And so this is the contribution of s tau coming from this region, and this is the contribution of rho coming from that region. So there are two regions here, and this is the contribution. This is the contribution of the first part, that is the contribution of the second part. And all other things just cancel out for tau and sigma because they are the same. So you just need to understand what is this, and the rest is very, very easy. So what is this? So this gives us mi minus m prime ai, sorry, this should be c minus ai minus 1 plus mi minus m double prime ai minus c. What did we do? We just wrote this as c minus ai minus 1 plus ai minus c. So if you do that and do the algebra, you'll get that. Okay, and therefore, as we said, there is no need for absolute value, but I will put it. This is less than equal to mi minus m prime mi minus m double prime absolute value ai minus c. So we just used triangle inequality. This is already positive, so we don't disturb it. We just use triangle inequality. Yeah, so yeah, I mean, you can get rid of absolute values in various places because of course mi is at least as much as that, so you don't really need to put absolute values, but I'm putting it. But note that this thing is at most 2k because we have that supremum of the absolute value of f is at most k, so mi is at most k and m prime is at most k, so their difference can be at most 2k. So this is a wasteful bound maybe, but who cares. This is 2k c minus ai minus 1 plus 2k ai minus c, which is equal to 2k ai minus 1, which is at most 2k norm of tau. because norm of tau is maximum of all these quantities as I varies from 1 to n. So of course this is going to be at most the maximum, and therefore we have that, and this proves our lemma. Okay. This lemma has an immediate corollary. Corollary is again, let f be a bounded function the YouTube forward button is your friend. And let tau be a subdivision of a comma p. Let rho be a subdivision of again a comma b obtained by inserting r points to tau. So in the previous lemma we inserted only 1 point, now we are inserting some r points. R is some, of course, non-negative integer or positive integer. So then s tau minus s rho, no need for absolute values, but I will put it, is at most 2kr norm of tau. And it's just induction. You do this sequentially. You, instead of putting r points all at once, you put 1 point, then another, and you'll get that. So fine, we have that, and now we can prove what is called Darboux's theorem. What does it say? Well, it says something very, very meaningful. So it says that for all, okay, fine. So we have let f be a bounded function. Then the lemma says that for all epsilon greater than 0, there is delta greater than 0 such that if norm of tau, okay, so such that norm of tau less than delta implies s tau minus the upper integral there is no need for absolute values, but I will put it, is at most epsilon. So it says that if you take a fine enough subdivision, given an epsilon, if you take a fine enough subdivision, meaning its norm is at most some delta, then the upper sum corresponding to tau approximates the upper integral very well, meaning up to epsilon. One can express this in a suggestive way by writing limit norm tau going to 0 of s tau. This is equal to that. So basically I should have just written it, and what this means is this whole business. Okay, so let's prove that. So let epsilon greater than 0, and we need to find a delta such that this holds. Okay, so fine. Since infimum over all subdivisions of the upper sums is this chi by definition, there is some sigma a subdivision such that S sigma minus this upper sum is less than epsilon by 2. Right, so this is immediate from this. Okay, so say sigma is that, and here's the thing. So we construct a delta. So let delta be equal to this number, and you'll see why we are defining it in this fashion. Well, if n equals 1, then there is a problem here. So let me put here. I mean, this is even better for me. So yeah, great. So we have that. And now, so we'll show that this delta is the delta which satisfies this. Okay, so to do that, now let tau be a subdivision such that the norm of tau is less than delta. So we will show that this is the case, which will finish the proof. All right, fine. So now let rho, to do that, let rho be the subdivision of a comma b obtained by inserting a1 up to an minus 1 in tau. So basically we are inserting the points of sigma into rho, but we do not insert these two because they're already present in tau. Sorry, we are inserting the points of sigma in tau, and we are not inserting the endpoints because they're already present. So we are inserting only these 2 points. In fact, some of these may not 2 points. Sorry, all of these n minus 1 points, and some of these may be present in tau. Well, that's okay. That doesn't matter. So the point is that we are inserting at most n minus 1 points in tau to obtain rho. Okay, so then by the previous lemma, we have S tau minus S rho is at most 2k n minus 1 norm of tau, which is at most 2k n minus 1 delta. Well, I did not say what is k here, but I hope you understand. So k is what it has always been. K is supremum of mod fx over the entire domain. So that is k. Sorry about not mentioning it earlier. So this is at most that, which is equal to 2k n minus 1 epsilon by 4 n k, which is equal to epsilon by 2 n minus 1 by n, which is less than epsilon by 2, and this is all that I wanted. Okay, so this is less than epsilon by 2. Great. Which implies that S tau minus S. Okay, how do I write this? So S tau minus S sigma plus S sigma minus S rho. Yeah, this is fine. This is less than equal to epsilon by 2 plus and nothing. So that's it. I mean, all we did was we just added and subtracted that guy. So we have this because we have that. But the point is, Rho is a refinement of sigma. Rho is obtained by adding the points of sigma to tau. So of course rho refines both sigma and tau. It is the common refinement of sigma and tau. It's basically what it is. So this is a positive quantity because this is finer than that. So this is a non-negative quantity at the very least, which implies that we have this. But now if we use that also, basically add this to that and that to that, we will get, which implies s tau minus the upper integral is at most epsilon, which is same as saying that the absolute value is at most epsilon, because of course this is not less than that. This is the infimum over all subdivisions of the same quantity, so this is at least as much as that. So we can just, if we want, we can put absolute values. So that is the statement that we wanted to show, and we have shown it. So that is Darboux's theorem. And why is it very useful? It allows us to choose subdivisions of our choice now, as long as we, maintain that the norms are going to 0. So here is one way to, here is one enunciation of this this fact, what I was saying. So again, let f be a bounded function. And sigma k be defined as a naught, which is equal to a. The second guy is a naught plus b minus a by k. This is a naught plus twice of b minus a by k, dot 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 a n a k. So for each k we define the subdivision. Let's see what we are doing. So this is a and this is b. We are saying just divide this into k equal parts. Each part will have length that. Just divide into k equal parts. So you have sigma k, and clearly then the norm of sigma k goes to 0 as k goes to infinity. So the conclusion is that s sigma k converges to the upper integral if k goes to infinity. This is immediate from Darboux's theorem. So this is the reason. I mean, now we have a handle on what kind of subdivision that we started with, and now if we understand f sufficiently well, then we can compute s sigma k, and hence we can find the limit. This is just a matter of now finding the limit. So we'll see an example just in a moment. Before that, let me also give a corollary of Darboux's theorem. So corollary of Darboux's theorem is, let f, again it's a bounded function, all right, and c be some point strictly between a and b, then this upper integral is, I'll write something which I will explain. So a priori this does not even make sense. We defined the upper integral of a function on its domain, and we just, we have this notation for those functions whose domain is the closed interval a comma b. So what does this even mean? This is just a shorthand for upper integral of f restricted to a comma c, and this is the shorthand for upper integral of the function f restricted to c comma b. So again, even if I did not say that, I'm sure it was clear, but it is technically important to say this. So it's saying that you can kind of break the upper integral into two parts. If you have this is your domain, then you find out upper integral on the first part, find the upper integral on the second part, and just add them. You'll get the entire upper integral. So that's very nice. And why is that? Basically choose subdivisions of this and subdivisions of that such that both of their norms go to 0. As so for each case choose a subdivision sigma k of the first part, tau k of the second part, and call rho k as this entire subdivision obtained by just concatenating these two subdivisions. And we are choosing sigma k and tau k such that as k goes to infinity, the norm of sigma k and tau k both go to 0, and therefore the norm of the entire thing, of the entire subdivision, also goes to 0. So then it's clear that S of the concatenation is S sigma k plus S rho k, and sorry, not rho k, this is tau k as I wrote, so that was tau k, this was sigma k. So if you take limit, and then this becomes the, you know what's happening. So it's something that we have now proved. And now lastly, let's take an example. So let f be this function. So the graph of the function is it's just this line. So then we want to compute the upper integral. Fine. So what we will do is I'll remove that one. Is it a 45 degree? No, it's not a 45 degree line. Yeah. So we'll take the subdivision of the following sort, the equipartition sort. So just fix a k, and then what is this length? This length is 1 by k. Took a long time to draw it. So that is how we have the subdivision. This is the kth subdivision, call it sigma k. So S sigma k is what? S sigma k is this value times that length, this value times that length, and then that value times that length. So the value is 1 upon k times 1 upon k plus 2 upon k times 1 upon k plus dot dot dot. How many times we'll be doing this? We'll be doing this k times. And this is equal to 1 upon k square summation I equals 1 to k of I, which is 1 upon k square k into k plus 1 by 2, which is half of 1 plus 1 by k. So therefore limit k tends to infinity, S sigma k is half. And what is the area under the curve? If I pose this to a high school student, then he will immediately tell me that the area under the curve is half, and that's what the upper integral is also, as we calculated. So in this case, actually the upper integral does converge to the or it becomes equal to the area under the curve, although we haven't even defined what we mean by the area under the curve, but at least it is an intuitive concept, and we can appeal to it. So the upper integral turns out to be half. If you calculate the lower integral, it will also turn out to be half. And yeah, so everything that I said was about upper integrals, but you can prove exactly the same theorems for lower integrals. You can state them and prove them for yourself, exactly the same proofs. So yeah, and you'll find, so the lower integral will also be equal to half. So in this situation, the upper and the lower integral coincide. So yeah, so we can now compute things basically. This allows us to compute things. Maybe you can take the following as an exercise. Exercise is to compute the upper integral and lower integral of this. Right. So I guess that's it. As usual, like, comment, share, subscribe. I also have Patreon. The link is next time.